Hello, everyone. Can you hear me okay? Hi. So yeah, I'll be talking about TLS mostly today, and about how you react basically when you're faced with a custom TLS stack, so something which is not standard OpenSSL based or things like that, and how we built a tool with a guy I've never met basically from over in Europe, which is an offensive TLS stack basically based off of scapy. So, the usual, who am I? So basically I'm a security engineer, work at Citrix, and I'm mostly interested in, low-level topics, like crypto, fuzzing, and exploit dev, and the usual disclaimer. So generally the agenda, I'm going to try and keep it pretty practical and not go into too much crypto depth. So I'll try, most of the stuff presented here will be, reproducible and practical. And so I'd just like to have a quick chat about the TLS attack timeline first. What has been shown, what has come up in the last few years, and what are the problems with it. And mostly, the difficulty in reproducing those attacks. Basically, when you've got something new which comes out in the news or not in the news, but something major on TLS, the difficulty of replaying it. I have a really quick refresher on TLS. I'll try and keep it short. I don't know how familiar you guys are with the protocol, but I'll keep it pretty short. And then I'll talk about scapy SSL TLS, which is the offensive stack, which lives above scapy, and why we built it, what are the goals of it, and what's its purpose. And obviously I'll do a demo of it, and then I'll go a bit more in depth into what to look for basically in custom TLS stacks. So how to fingerprint them, how to look for side channels, and a little talk about fragmentation. And then I'll talk about how scapy SSL TLS helps you basically by making encryption transparent, basically for abstracting the crypto part from the actual protocol, so that you can attack what's inside the clear text packet, as opposed to handing crypto and HMACs and ciphers and PRFs and all that stuff. And then I'll just do a quick demo of detecting poodle and fragmentation, obfuscation through TLS. And if I've got time, I'll talk a bit about the fuzzing capabilities. So a quick introduction about TLS. It's And why we decided to build this is that, it's such a critical protocol to the internet, as everyone knows. It runs everything. And the thing with it, it's that it's got very few alternatives. There's a session layer protocols, which provide security for other stuff. There's more or less nothing out there, so we'd better make sure that it's okay and that it works well. And the thing is, it's so complex, right? It's super complex. Until I'd written this stack, I didn't realize at which depth it was complex and how many edge cases it had. But, it's got 3 key exchangers, it's got over 100 ciphers probably, multiple PRFs, a ton of hash functions, and the state is insane inside the state machine, right? So the good thing is that it's under scrutiny, right? It's like there's a lot of people working on it or researching on it and coming up with new alternatives to do things and new attacks on it. But when you're on the defensive side, you're seeing basically a growth of the number of attacks and a lack of tooling, right? So you're seeing these new attacks come up every few months, and I'm really talking about protocol level attacks, not implementation level. And you've got a lack of tooling. You've got all this stuff coming out with no proof of concept, nothing, and you're kind of trying to figure out if a product is affected, if something you're in charge of is affected. And yeah, the attack tools generally are ad hoc, right? You'll get, worst case, you get nothing. You get a paper with some maths and stuff which you have to go through. And best case, you get some Python with a bit of OpenSSL custom stuff which you have to compile, which is a pain. All right, so just a quick view on the TLS protocol level attacks. Just the timeline mostly. I won't go in detail into each of them. So as I was saying, the protocol's under scrutiny, which is great. And you can see that it's been under scrutiny even more since like roughly 2013, 2012, and with a massive improvement in the number of protocol level attacks. And as we all know, OpenSSL also has got a ton of implementation bugs which are coming out, which is starting to calm down, but you've also got that to deal with. So if you look, this is roughly all the attacks I could think about, I could remember, which I tried to put together, through some PowerPoint foo. But basically, like until 2013, you didn't have a lot to care about, right? And it probably wasn't a good thing, as it shows now. And since 2013 and accelerating now, you get more and more of this stuff. And not only do you get more and more of this stuff, but you get more and more complex stuff. Like Logjam asks a lot of pre-computation. Sloth, what came out recently, is looking into MD5 collision attacks and stuff used inside the protocol. So all that is complex stuff. So yeah, as I was saying, the attacks, they increase in frequency, meaning now you've got very little turnaround time to deal with them, and in complexity. And you generally deal with two classes of them, which are either at the protocol level, which is the worst case because then the protocol's broken, we have to find fixes and workarounds and all this stuff, or at the crypto level. So, just a quick note about reproducing them. So, again, you're going to have to spend some time trying to understand the attack properly. So you've got a paper, you've got a couple of hours, you're going to read through it, and figure out what you can do with it. And you need to figure out, most importantly, the practical impact of it, as opposed to the theoretical one. There's a big difference, right, on your product. And more importantly, you need to focus on reproducibility, because you need to reproduce it hopefully for people in dev and QA, because you want to be able to provide them something they can work on to actually fix a problem, right? And provide something actionable which the QA guys can test with and actually do some regression. And right now I don't think there's any tool in this space, or there wasn't until a couple of months back, which would allow you to do this. Another thing is mostly with with response, right? If any of you deal with response, you're going to get an attack, and then in a couple of hours you're probably going to get a customer response case, right, asking you if you're affected. And the thing is that customers, they don't always understand the practical impact of it, and it's normal, because you as a security engineer who does this all day, it will already take you a few hours, a few days to figure out take out the FUD, right? And so the thing is, you've got this customer response, and you're going to have to provide, or your response team is going to have to provide an answer within the next couple of hours, right? Or next couple of days at best. And roughly, you had two solutions until now. It's like, do you do crypto code review? So the thing is, like, if you're working on a TLS stack, which is custom, and if you've got sources, then you can perform code review. The thing is, which is super hard with a custom stack, is that you've got a lack of comparison point, right? It's not like you're looking at OpenSSL and you're going to compare it with a patch, or you're looking at, I don't know, OpenSSL against something else. So that's pretty tough. And again, when you're looking into crypto code, it's quite hard to get the full picture, right? When you're looking at a tiny routine, wondering, okay, if this is not prime, what's going to happen? Inside, 10 routines of crypto stuff, it can be quite difficult to get a good idea of what's happening. So again, you can write a POC, but you had this lack of tooling, so it meant you had to write some C code, extend OpenSSL, tweak it, write your custom version to let it accept, a various number of arguments and all this kind of stuff. Because the problem is you've got a big difference between, a security focused tool and, a general dev tool, and, that's a good thing, right? Because dev tools, hopefully, if they're well made, they give you a full bunch of safeguards which prevent you from screwing up the length, screwing up your cipher, your crypto, all these things, which you don't need, or those safeguards prevent you from achieving the actual attacks on this. So the idea is, if you build a POC, it's reproducible, and you can use it in QA, and you can use it in regression, right? As opposed to doing a code review, well, you'll have an answer possibly, and maybe you're wrong. So I'll do a super quick refresher on TLS, just so that we're all clear on the fundamental concepts, because in the tool we wrote, you still have to be familiar a tiny bit with TLS, how it works, the different layers of it, the different subprotocols and all this stuff, because it is a complex protocol. So yeah, as I said, TLS, session layer. So it does nothing basically except provide integrity, authentication, and crypto. Well, that's not nothing, but it only shifts bytes. And its main reason is to perform a handshake and then provide crypto, based on that handshake. So you're going to negotiate a set of ciphers, of MACs, of secrets, and that's going to allow them to build a crypto tunnel, basically, based on symmetrical ciphers. And the thing is, that it's fully transparent to the protocol, again, right? Your protocol doesn't care. You can pipe anything you want through it. Another thing is get quite a high round-trip time. So you need at least 4 packets or 2 round trips to create a handshake, which is quite a bit compared to other stuff. It also offers session resumption, and that's quite an interesting edge case. It means that you don't have to go, since the handshake is so expensive, you can resume a TLS session. But that resumption is not authenticated, right? It just assumes that both sides know the master secret, which is the master piece of material used to derive the keys, right? And it can authenticate both client and server, right? And provides integrity and confidentiality. So also what's interesting is that it relies on TCP for packet delivery and ordering, right? So that's, for TLS, it's fine, you know. TCP will take care of ordering your packets, putting them in the right order and giving them to your cipher and to get them out. The thing is, if there's a version of TLS called DTLS, which runs on UDP, right? And DTLS can't rely on TCP for packet ordering, so it's got the whole notion of having sequence number, and it also has secret offsets and things like that. So you're coming back to a case where kind of you're close to IP fragmentation in the old days, where you can have overlapping offsets with, you know, all this kind of stuff. All right, so the message format. So TLS, roughly, it's actually a collection of sub-protocols. So you're going to have the handshake protocol, which is in charge of negotiating the parameters, in short, of deriving the key material, of having extensions and all these kinds of things. You've got the change cipher spec, which isn't really a protocol, it's just a byte. It's a single byte, basically, which is encrypted under the current cipher scheme and which signals a transition, right? So when you get a change cipher spec, the stack knows that it needs to change crypto operation, right? It's the last packet encoded on the current cipher standard, right? And then you switch basically to the new cipher. So typically during the handshake, you'll get a change cipher spec which is in clear text, and the next packet following will be encrypted under the negotiate parameters, right? And then you've got alert, which is another sub-protocol. So all it does, alert, is error handling. So you'd probably skip that one and think, okay, that's fine, it just does error handling. The thing is, it does error handling for crypto stuff. So it can't leak too much information, and there's been problems with it in the past, right? And you have to be very cautious of what alert leaks. And finally, application data. So that's just the layer which will shift your data across, which is the most complex from a crypto operation, but it has no state at least, or only cipher state, so it's kind of simpler. And so the thing to remember is that each of these sub-protocols are encapsulated in what's called a record header, right? So the record header is just a really simple little blob. It's for 5 bytes. It will tell you which TLS version you're using, the length of what's coming after it, and the payload type, so basically which sub-protocol follows. So, it looks really simple. It's in charge of transferring the sub-protocols. And it's always clear text, right? So you've always access to that record layer because you always need to know basically what sub-protocol comes in after. And it's always clear text. So it means that, in TLS, another little quirk is that the payload length is never is not protected, basically. Except by when you've got a cipher, it will be aligned on a block boundary and the padding. But basically your length is out there. So TLS does allow you, though, to play with padding to compensate that to some extent, but it's not widely deployed. And records, they're stacked basically inside a packet. So you've not got no direct mapping between a TLS record, which is a sub-protocol portion, and a TCP packet. It can be in multiple packets, it can be in one packet, and all this. And you can control that at the TLS layer through fragmentation, which I'll talk about later. So a tiny bit more on the handshake. So it's in charge of negotiating compression, right? So TLS can perform compression before it does encryption, right? Which is definitely not a good idea, and that's why no one does it anymore, right? It exposes a whole bunch of problems through the compression layer, which can leak stuff about the clear text. So that is gone. It negotiates crypto parameters. So which key exchange are you going to use? Is it going to be RSA, elliptic curve Diffie-Hellman, or Diffie-Hellman? Which cipher are you going to use? Which signature algorithm are you going to use from time to time? And things like that. And which HMAC are you going to use, and all these kind of things. And most importantly, it's in charge of initiating crypto material. So TLS comes with a custom pseudo-random function, right, which is seeded by all this stuff. So it will take a bunch of randomness, a bunch of static portions, master secret, which is generated basically through the key exchange mechanism, through RSA or Diffie-Hellman. And that is used to generate a master secret, which in turn is used to generate all the keys which are used during crypto operation. So the thing is that the keys are asymmetrical in TLS, right? You've got a key from client to server and one from server to client. And same for the HMACs and same for all this kind of stuff, right? So the handshake has got a good role in there doing that. Another really important role it's got, it's in charge of ensuring that the handshake is free of tampering in transit, right? So you'd think, okay, in TLS, let me change the cipher by another version and just pass the packet when I'm a man-in-the-middle. Obviously, you can't do that, and thanks a lot, otherwise the downgrade would be trivial. So you've got this little message, which is fundamental, which is called the finish message, which is encrypted, and which is basically a collection of all the hashes of the previous messages. And so it's transferred, and then it's checked on both sides. So if both sides, see, hey, we've got a different hash on all these previous messages, you've got tampering, and that it's not going to work, right? Another important thing is that it's really extensible, right? So you can extend TLS through a bunch of extensions. And you can basically, it's got a ton of extensions. Each time you do a handshake, you're going to say which elliptic curve format for your points you support, which curves you support, which URL, which hostname are you trying to reach in the case of SNI, which upper layer protocol are you going to use for HTTP2, for Speedy, and all that stuff. All that is done in extensions through TLS. And so a bunch of handshake quirks, basically, right? So the handshake has a max size of 2 to the power 16, right? And the thing is, the max fragment size in TLS is 2 to the power 14. So it's 65,000 bytes, right? So in practice, the handshake can be fragmented across multiple records, meaning that your stack has to be able to do reassembly to fully understand a message. And the thing is that very few stacks out there do that because you don't really need to, because 65,000 bytes is a lot for a single message. And yeah, I'll talk a bit of the side effects that this can have. Some messages basically can have arbitrary trailing data. So as I said, you can have extensions in your handshake. But the thing is, so that to ensure compatibility, the extensions don't have to be understood on both sides. So this means that you can just throw garbage data inside at the end of a handshake and it will work fine, right? And this is fundamental because this was what was used in Sloth to be able to compute the pre-image collisions on MD5 to allow performing the attack further down. You don't necessarily need a certificate, right? There's all these weird stuff which is never used, but you can do anonymous RSA, DH, and ECDH, where basically the server side will generate keying material on the fly, right? It will generate a certificate on the fly for you. And also you can have, this is a really weird quirk, and it's a really pain to implement and to parse, but you can have stacked handshakes, basically, which is, if you saw my previous diagram, you had a record and then a handshake and then a record and then a handshake and then a record and then a handshake. There's this really weird quirk where you can concatenate a bunch of handshakes together inside a record, and Java does that. So this is just a quick rehash of the application data stuff. So the application data, which is just the layer in charge of transporting things, it's in charge of encrypting and authenticating packets, right? So what happens is that your clear text, say your HTTP GET request, goes in through the stack, and then there's an HMAC which is calculated off of that, right? So it's just a MAC to ensure integrity of the clear text. And then the thing is padded, right, with a bunch of bytes. So the important thing to understand here is that the padding is never protected by the HMAC, right? So it's not authenticated. So this was the whole problem with Poodle, with all these things where you can just flip bytes in the padding because it's not authenticated by the HMAC, right? This is all the MAC and encrypt problem, right? And obviously, yes, there's no padding, for anything which is protected by a stream cipher because they don't have a block size. Okay, so all this to take us to scapy SSL TLS, right? So the idea behind this was like, all right, so we've got all this stuff coming in. How do we deal with it? How do we reproduce stuff? How do you learn about TLS? How do you develop new exploits, new attacks on it? It's you need some kind of stack which helps you do that, and this was the story about why we built it, right? So scapy, if you guys are familiar with it, it's just a library basically which is great because it allows you to model a network protocol, and it will dissect. It will basically allow to craft packets and break them and dissect them. So get you a representation out of the bytes. Yeah. So scapy SLTS is just that. It lives above scapy, and it just is in charge of allowing you to create packets and allow you to dissect packets and view what they are. So the thing is, we try to make it stateless as much as possible. And that's a real pain to do because TLS is so stateful by default, right? It's a massive state machine. That's all it is, and it does stuff. But the thing is, if you want to exercise the code at the state machine layer, you have to be stateless, right? So scapy allows you to do this stuff, to do these kind of things. It allows you to craft packets and dissect them. So meaning that when you get a response from a server, it will be able to dissect it for you and provide you the individual fields which make sense, which you can then reuse, right, yourself. And it does crypto session handling. So as I was saying, you shouldn't have to bother about all the crypto operations. That's kind of abstracted away. But it provides hooks into it, so you can modify the padding, you can modify the MAC on the fly and do some stuff like that. And then it can do a bunch of sniffing, but it's not its first purpose. So why bother, right? As I was saying, TLS stacks, they're built to be robust, and thanks for that to all the devs who actually, build those stacks. They're really robust. But as a security engineer, that's a pain because you can't modify all the parameters you need in order to reproduce stuff, right? They enforce input validation, and they tear down the connection on error, and basically they're not flexible at all. So the goal of this is to create a stack which is easy to use, basically, mostly easy to install, right? Because if you have a problem installing it, please file a bug. This stuff should just work. So if we haven't done the job properly, just file a bug. It should simplify basically the discovery and exploitation of TLS vulnerabilities that come out, or basically in a response scenario, just help you figure out if it's a problem for your product. It allows you full control of any TLS field. As I said, it tries super hard to maintain no state. So that, for example, you can send a record within an alert and then send a handshake on top, right? That makes absolutely no sense from the TLS state machine, but you can do this. And so you can look for state machine bugs, and there are some. It hopefully has good documentation and examples, and no checks are enforced, right? So it's not for use by dev. There's no certificate checking, no signature checking, there's nothing, right? No length checking, anything. So all this is basically, all you want to do is that it's not necessary. This is the stuff you're looking for, right? And it tries and have sane defaults and transparent encryption. So I won't go over the full support of what it does, basically, but pretty much anything which is from SSL v3 to TLS 1.2 works, or should work. It supports all the major, key exchangers, so you can do RSA, ephemeral Diffie-Hellman, elliptic curve, all this stuff. It does RSA and DSA signatures if you need, and it can do any record and extension, but that's more by TLS design, where I was saying you can throw any random bytes at it, right? And it can do some client certs. So the only thing missing is basically the authenticated ciphers, so ASGCM and CCM mode, because we rely on PyCrypto and it doesn't support that. So, if you just want to install the stable branch, basically, it should be as simple as pip install scapy SLTLS. That should pull all the dependencies and you should be done, right? That's all the links to the other, Git repos, but you don't really need that. So the concept is you're going to start scapy and it's going to bring back a prompt to you, and I'll show you in a second, right? And we made sure that all the classes start with TLS, so it should be kind of easy to explore. You can just autocomplete, and it should allow you, give us sufficient stuff. If you're familiar with scapy, basically this will be like a no-brainer for you. It will be super simple to use. It's exactly, it just lives on top of it, so it's the same stuff. If you want to check what fields are available, you can do ls on the thing, and it will tell you, hey, you need to add this size of 2 bytes and etc. So the only thing is that we added, a small proxy object around a socket called a TLS socket, which is the thing used to send and receive data. And all it does basically is it puts data in shape for you. So you can send it, a packet instead of bytes, a scapy type packet, and it will transform it to bytes and send it out. And it does the thing the other way, on the other way. And so, you build packets, scapy style really, just by adding the slash in front of them, and this is what you do, right? So I'll just show you really quickly. So I've got an OpenSSL server basically running TLS 1.2, and I'll just show you guys a quick example of what you can do. So this will drop you in a shell. Is this big enough? Is this big enough for you guys? Or? Yeah. All right, so basically it just drops you in a shell, and then, right, this will give you a list. So the font is so this will give you a list basically of all, available records and things. And so the idea is that you can build packets pretty simply, and that's the only, manual demo I'll do. Right, and this just built you, a client hello. And you can do that with anything else. And so basically the idea is that then you get this output which can show you. So basically it will show you, right, the dissected payload. And, you can interact with any type in there, meaning that, you can change anything in there, the session ID, the cipher suites, the compression methods, and all this stuff. This doesn't seem like a big deal, but it was something which I don't think existed before. And the thing is, it will pre-compute all the boring stuff for you, meaning it will generate some random bytes, get the Unix time, choose a default random cipher, calculate all the lengths, and all this stuff is done for you, right? Yeah, so here I'll just show a quick example of basically sending just a client hello to a server and getting a response. So this is all the code you need, more or less, to do that, right? And a lot of it is just, creating a socket and doing this kind of stuff. Right, so here I just sent it out to my OpenSSL server, right? And what I'm showing you here, I thought the screen would be bigger, so this is a bit, is basically the server response. So what you get back is you get back a server response with a whole bunch of fields with which you can interact again, right? So if you want to dynamically check, if the session IDs generated are properly random and stuff, it's stuff you can do. You can collect all this stuff. What's interesting is that you also get certificates back, and they're parsed in their SN1 representation. So you've got access to all this stuff within the cert. You can check for extensions and stay and check for all these things, the signatures, and validate all that. Another interesting part, basically here, is that it will give you all the elliptic curve Diffie-Hellman server parameters, right? So all the Diffie-Hellman stuff, and you've got straight away access to that. So you'll have access, to the prime. To the group size and all these kind of things, to the signatures, to the name of the curve, and all these things. And just to show you again, there's basically something which will maintain all the history of the packets for you, which is called which is a context. So it holds the context for the whole TLS session. And what it does is that it's pretty handy because it will give you every single parameter which has been negotiated during the transaction. So here, for example, you can see here, this is the curve point from the elliptic curve Diffie-Hellman exchange, right? Showed to you as an equation. And, so you can act on all this, basically. You can get back the point back and do some calculation on curves and all this stuff, right? It also gives you, the pre-master secret. So all this, the pre-master secret, the master secret, you can then derive all the keying material, or you can interact with it, change it, and tamper with it, and do all this kind of things. Obviously here, there's not yet any MAC encryption and IV stuff because the connection hasn't gone through yet, so the parameters haven't been generated. Okay, so I just want to show you really quickly how you can also craft extensions and why. This is pretty much the same thing as just before, except I'm going to add a bunch of extensions. It's not very impressive. You're just going to see in Wireshark there's a bunch of extensions. But the thing is, why it's super interesting is that TLS extensions, they force the server to perform different code paths. So the thing is, when you can play with extensions, you can start fuzzing them and exercising new code paths basically on the server side. And that's why I'm showing you how to craft them, because it really allows you to get into the extensions and fuzz them to a level that can, hopefully or unfortunately trigger a server-side crash, right? So I'll just start Wireshark on this and then go back to my shell. So here again, Here I'm just going to show basically a client hello. So I sent a client hello with an ALPN, an SNI, and a fragmentation size that I wish to negotiate with the server, which I'll talk about that extension in detail a bit later. And so if you look basically here, you've got control. We crafted a packet where you've got full control here of the server name. And so, you can do a whole bunch of stuff on this. You also have control of the length and all the variable different fields. You can pretty much put any bytes you want anywhere in this packet, which means that you can change the length of the list, change, the type, etc. of all this stuff. Same here for ALPN. I negotiated HTTP2 above this. So same thing, right? You can go after whatever you want in this stuff. And here I sent a fragment length, which is invalid, right? This shouldn't be E9. It can only be a value of 1, 2, 3, 4, 5. So it was just to show basically that here you can throw any bytes you want inside those extensions. So another thing I want to show you is the transparent traffic decryption. So here what I'll do is, again, this is all the code you need, right, to speak with a server and to encrypt data to it, right? So I'm just going to encrypt a GET request back to OpenSSL. But the thing is here, it's just going to show you that all the keying material, you're going to get it back, and you're going to be able to have a look into it. So you can poke into the randomness of IVs, of all this kind of stuff. And what I'll show about later is how you can actually tamper with the different phases of this inside the encryption stuff. Right, so here, So here basically you got a response. This is just, the standard S server in SSL, which just responds with what ciphers and etc. So you can see that you got a 200 OK, so you got a response here. But what's interesting basically is here, all this is exposed. Again, programmatically, you can get access to all this. So you've got actually access to the IV, well, the explicit IV, because it's TLS 1.2, right? The MAC, the padding, and the padding length, which are all the fields which are the metadata for your data, basically, which are encrypted inside the encrypted channel. And again, if you look at the TLS context, you're going to have, so here you can see that you've got the elliptic curve private key for you, basically for the client, as well as your public key, the curve you're working on, the server-side stuff, and you've got the pre-master secret, the master secret, which has been calculated through ECDHE, and then a bunch of random bytes, right, coming from the server, and then finally your encryption keys, right? So potentially you could use this, and extract this data, and maybe decrypt it with Wireshark and do all this kind of stuff further. All right, so now, I've showed you vaguely the capabilities of the tool. What I want to show a bit further is what you want to look for. So say you're either in response or penetration testing or having a look at those stacks, if you encounter one of those stacks, just what to have a look for. And some of this will be pretty basic for you if you know TLS. Some of it might be a bit more surprising. So, you have to do basic recon. So what TLS versions are supported, what ciphers, what compression methods, which ordering of ciphers, etc. I won't spend a lot of time on this because this is well covered and it's pretty simple. There's a lot of tools out there which can do it. Another interesting one is that you can try and fingerprint the TLS stack more precisely. So one thing is that generally the custom stacks I've seen are generally forked off something at some stage, right? And the thing is that those various baselines have different behaviors at the time, and so you can try and fingerprint the stack to figure out, I think you can probably get down even probably to the major version number of what the stack can do. I haven't really researched further into this, but you could imagine having a tool similar to POF, which fingerprints, or Nmap basically, which gives you a fingerprint of the TCP stack or what host you're running. You could probably do the same thing here with TLS. So for example, OpenSSL, depending on the version, will add an empty plaintext fragment, right? And I don't think other stacks do that, meaning it will just send an empty string, an empty blob, which will be encrypted and pass through. JSSC, as I said, has the concept of a stacked handshake, and so that's something you'll only see with that. And also another one you can figure out is you will get a different alert type when tampering with the finished message. So the finished message, as I said, was a hash of all the previous packets and stuff, but it's got a small header, which is about 5 bytes, which is, just a bunch of it's a handshake, basically, header. And when you tamper with that, you will get a different alert message depending on the stack from time to time. So, there's probably more research to be done in this space, but I think it's stuff which can be done, definitely. So another thing you want to look into is actually the state machine. So the thing is, this is really a tricky testing part, and it's really boring and tedious to do. The thing is, it's mostly manual work because you're going to try and trick the TLS state machine into an invalid state. And the thing is, it's mostly manual state, and your good knowledge of the RFC and of the state machine. And I'm trying to think of ways how to automate this, but they might not need to, because the guys from INRIA in France, and I think they cooperate with other people, but basically they brought out Flex TLS a couple of months ago, which basically allows to test for these state machine style problems and basically can give you a really good starting point for manual testing. So it's a really good tool. It's based off my TLS. It's their verified implementation of TLS. They're the guys basically who find all the protocol level attacks on TLS. And yeah, it will exercise your state machine, and it's the only tool, open source tool at least, that I know which allows you to do that. And then it basically lets you drill down with scapy TLS if you want to on the areas it has identified and look further in. And the thing is, those stacks, they've got a lot of legacy stuff. So for example, one thing I encountered maybe a couple of years ago or a year ago was server-gated cryptography. And if anyone has a clue of what that is, but basically it's a really super old mechanism where it's based on the export stuff, and where you could your client could renegotiate stronger ciphers based on the certificate type returned by the server. So that stuff is still out there probably in some stacks for some reason. All right, on to Diffie-Hellman. Generally, an elliptic curve, Diffie-Hellman, I put them in the same bucket. So you want to look at the group size. All that's pretty simple because now you've got access to all the prime numbers, the field size, and all these values. Probably primility check. You want to look for subgroup confinement attacks if possible, and the signature algorithm used. Another thing you can do from the client side is basically send just a bunch of random values in there and see what happens. Right? Now it's pretty trivial to do. So scapy TLS uses tinyEC for elliptic curve calculation. So that's a library basically which allows you to do elliptic curve, but again without any enforcement. So you can perform arithmetic off curve and all this kind of things. So it integrates pretty well with scapy TLS because you can actually drill down to the elliptic curve level and send it back through scapy, which is helpful at times. So I'll talk about side channels really quickly, but that's a more known problem, so I won't bother too much. So when the pre-master secret is decrypted, basically TLS mandates PKCS1 v1.5 for padding, which is a padding scheme, etc. And Bleichenbach has showed, really in '98, that this padding scheme, once you've got a padding oracle on it, you can basically recover the clear text. So the thing is, you generally want to check. You want to generate faulty padding for the PMS, send that through, and check if you've got time or response differences, due to invalid padding, because that would allow you to carry out this stuff. You can use a tool called PyBleach, which allows you basically to generate faulty padding. So all you do is spit out your PMS in it, which you gather through scapy, and then just generate some faulty padding, send it out, encrypt it, and send it back out to the server and see what happens. So again, a bunch of side channels, but more on symmetrical crypto, which are well known, well documented. So you want to check padding, and MAC must be constant time, because there's a whole bunch. Well, again, a whole bunch of side channels on that stuff, and the alert types must be identical. And yeah, another one is that you want to check that the stack actually does proper byte checking. So some stacks, I don't know if you guys have written recently, but will only check a bunch. So that was Poodle 2, for example, is that the stack only checked the 2 last bytes of padding as opposed to the whole bunch, which allowed, to expand Poodle from 256 requests to 65,000, right, for a byte. And the thing is, the MAC also can have the same problem, where the stack will check only 1 byte of the MAC or a few bytes of the MAC, and you definitely want to find that out. And same thing for the verified data, which is the hash which I was talking about in the finished message, where you want to make sure it's completely checked. Otherwise, the tampering in transit, you could try and find a collision or things like that. So, the idea is I'll show you how to do all this just in the demo after, where basically it's pretty simple to do, hopefully, with this stack, where you can, all this stuff will be pre-calculated for you, and all you need is to flip a byte and send it out and see what happens. Just a tiny word on DDoS. So DTLS is UDP, right? It's the TLS version running over UDP, just to really simplify. And if you look at it, it returns the certificate chain on the first packet, right? So the thing is, you're sending a DTLS hello message, which is roughly 64 bytes, which you can obviously spoof since it's UDP, and you're getting a DTLS response, which can be several kilobytes, right? Because it's a cert chain. So that's, a major problem. And the fix is inside the protocol, but it's a may, right? So you definitely want to make sure that your server, if overloaded, actually sends a hello verify request, which is it's just a small cookie. What it says is it goes, I'm not going to perform all this expensive, I'm not going to send all these bytes on the wire right now since I don't know who you are. Let me send you a small cookie, and you do your request again with that cookie, and then I'll give you the real response back. But you definitely want to check for that because, the amplification problem is massive here in this case. So yeah, I'll talk about fragmentation. So this is quite nice, actually. So the spec says that any packet above 16,000 bytes must be fragmented. But the thing is, you can choose any fragment size you want. And if you remember, as I was saying earlier, very few stacks support TLS reassembly. So this means that your end server is probably going to support it, but your middle box might not. So what you can do is you can fragment your packets, say make them 16 bytes, and send those across, and there's a good chance that your middle box will fail to actually rebuild it. So all the stuff like IPS, all the stuff which man in the middle is TLS, if it fails open, it can be vulnerable to this stuff if it doesn't do proper TLS reassembly. So one interesting thing is that from a client you can fragment your stuff, but you can also to some extent ask the server to fragment his stuff. So there's a small extension called the maximum fragment length negotiation, which allows you to say, hey, server, I only can read 512 bytes packet, so can you fragment them in your response back to me? Meaning that you can also control to some level the fragmentation which is sent back to you. And that kicks in generally at the just before the certificates are sent. So you could potentially ask your server to fragment again the certificates when passing them back to you, which would possibly defeat the middle box, right? And again, as I was saying, DTLS allows you to specify the fragment offset. So you can have stuff where you're going to send a chunk, and then you're going to have an offset which starts within the chunk again, and so you can overlap data on this again using DTLS. All right, so I'll just have a really quick talk about how you can make how scapy SSL TLS makes the crypto hooks transparent to you, and how you can touch the padding, how you can touch the MACs and the IVs and all this stuff. So it exposes a method called TLS to raw, and all its purpose to do is basically give it some bytes, a context, and it will return you the encrypted blob of it, right? So the idea is you give it your GET request with the context of your current session, and it returns you the encrypted version you can send on the wire, right? So pretty simple. The thing is, it gives you a few. So first of all, it will calculate all the crypto material for you, meaning that that crypto blob will have a correct MAC, correct padding, and all these things. The thing is, it exposes a bunch of hooks at compression time, pre and post decryption, meaning that if you register a callback, you can catch the state pre-encryption when the packet is still key text, so you can get the data with the correct MAC, the correct padding and everything, and act on it before it hits the encryption routine. Meaning that now you can tamper with padding and the MAC and all this stuff quite easily because you don't have to calculate them. You don't have to bother about keeping track of the PRF, of the various keys and all this stuff. You can just change this. So all this stuff, there's an abstraction called a crypto container, basically which is just an object which holds a reference to the key and to the MAC, the padding, and the padding length. And if you look at the tiny snippet below, I'm giving a blob of plain text with a context, and I'm calling a modify padding hook, right? And all this does is that it's going to flip a byte inside the padding and send it out. And see, so this basically allows you to test for Poodle in like, 15 lines of code if you add the socket handling and all this stuff. And you can do the same thing for the Mac, make sure all bytes are tested. You can do the same thing for the verify data. It allows you really to poke into the protocol. So it's super useful, as I was saying, to modify crypto state without keeping track, of the PRF, the ciphers, the MACs, and all this stuff. And it allows you to reproduce attacks which happen inside the crypto element. So I'll do a really quick demo of this. So basically, I'm just gonna so this is an example. So you can just find it on the web at the reference I was getting. So here I'm going to run it against. So here, basically, all I'm doing is I'm flipping a bunch of bytes on a TLS 1.2 stack, right? So what's happening is that, I registered that hook, as I was saying. I'm just flipping all the bytes inside the cipher, and, TLS 1.2 is not vulnerable, right? So this just works out of the box. Thing is, if I restart my OpenSSL server in SSL v3 mode and do the same thing, here you'll see that it's, the connection continues basically, regardless of when I've flipped the bytes. So that allows you to detect this stuff really super easily. And this is easy to provide to a dev team and stuff to do QA or regression or whatever you want to do. So I'll do a really quick demo on fragmentation, which will be the last one. So here again, all I'm doing is I'm going to create a packet, a client hello, and I'm going to fragment it on a 16-byte boundary, right? And you're going to see that in Wireshark, basically, Wireshark fails to rebuild that packet. And there's a good bunch of stacks out there which also fail to do the same thing. So here I just did a handshake, fragmented it in 16 bytes fragments, and send it across. And basically, you'll see that here, you can see that here, Wireshark only sees an encrypted handshake message. I don't know why it figures that out. But here you can see my 16-byte fragments here, which are failed to be reassembled as a client hello. Right, so here it means that the intermediate device has no knowledge of this and what's happening on the wire. Sorry? Oh, okay, yeah. All right, so this is so all I had for you guys. So basically, so this is mostly all I had for you guys. It was just to show, that this stuff, if you work with TLS quite a lot, it can really help you, prototype attacks really quickly and make sure that, know or not if your products are affected. It's not amazing stuff. It just allows you to get access to a whole bunch of fields that you couldn't before, and makes prototyping really much simpler. You get access to the whole bytes, the whole representative bytes inside, inside a TLS handshake and inside TLS itself. And it's really valuable. I mean, mostly I can speak for us. It was really super helpful in response, mostly. When you've got these problems which come out, you can prototype this super quickly, and you can get a black box view of your product and know if you're affected or not straight away. And that was pretty good. It can also help people, which are interested in learning and experimenting with TLS, basically, and just having a look, just playing around with it, because building packets is quite simple. So just a bunch of thanks. I'd like to thank TintinWeb, basically, who's the guy with me working on this in Europe, who started the project. I just contributed to it. If you find any bugs in it, we're definitely interested to hear it. Don't be shy. Just point it out on GitHub and just file it out. And if you want to speak to me, this is my GitHub alias, and that's it. Thanks a lot.